Here is a combined summary of the 2 pages. Large foundation models, LFMs, have become increasingly popular in recent years due to their remarkable performance across various tasks in natural language processing, computer vision, and other domains. However, their vast number of parameters and substantial computational demands pose significant challenges for efficient fine-tuning, particularly in resource-constrained environments. To address this issue, parameter-efficient fine-tuning (PEFT) techniques, such as low-rank adaptation (LoRA), have emerged as practical solutions. LoRA reduces the number of trainable parameters by employing low-rank matrices to approximate weight changes, making fine-tuning more feasible and accessible without compromising the model's performance. However, LoRA's capacity to represent a target model is strictly limited by the rank of the low-rank matrices, prompting the need for alternative approaches that achieve high-rank adaptation without incurring significant costs in terms of computational power, memory usage, and trainable parameters. To address this limitation, the authors propose circular convolution adaptation, C3A, a novel approach for PEFT using convolution. C3A leverages circular convolution kernels and their equivalent circulant matrices to provide a flexible rank, which is free of linear constraint by the number of trainable parameters, for the delta matrix. By incorporating the fast Fourier transform, FFT, C3A ensures better computational and memory efficiency than directly multiplying a delta matrix. The authors extend C3A by incorporating block circular convolution, which results in block circulant matrices, allowing C3A to achieve fully customizable parameter counts as well as adaptable rank configurations. Comprehensive fine-tuning experiments across diverse tasks demonstrate C3A's outstanding accuracy and memory merits compared to existing state-of-the-art methods. The authors also review related work in PEFT, categorizing existing approaches into 3 main directions: partially updating the pre-trained neural network, adapter-based methods, and delta-weight-based methods. They highlight the limitations of existing methods and the need for novel approaches that achieve high-rank adaptation without incurring significant costs in terms of computational power, memory usage, and trainable parameters. Here is a combined summary of pages 3 and 4 of the research paper. The authors introduce C3A, a novel prompt engineering (PEFT) approach based on circular convolution, which fine-tunes large foundational models, LFMs, efficiently. C3A adapts to the downstream task by tuning circular convolution kernels, representing the delta weight as the block circular matrix constructed from these kernels. Unlike LoRA, which uses low-rank decomposition and matrix multiplication, C3A's circular convolution operator achieves an efficient and lossless performance in LFMs. The authors overview the C3A method, highlighting its differences from LoRA. In C3A, the delta weight is represented by the product of circular convolution kernels, whereas in LoRA, it is represented by the product of low-rank matrices A and B. The total trainable parameter number in C3A is BD, which disentangles with the rank of the delta weight. Circular convolution has been extensively studied in signal processing and cryptography, and has been explored in machine learning for generating long embeddings of high-dimensional data and compressing heavily parameterized layers. Despite its success in small neural networks, circular convolution has not demonstrated lossless performance in modern LFMs. The authors propose that the intrinsic bias of circular convolution could serve as a regularization mechanism, benefiting the fine-tuning process. The authors introduce the notations used in C3A, including the circular convolution operator star operator, adapted weight matrix W, original weight matrix W0, and delta matrix increment W. They also define the activation vector X, post-transformation vector Z, and incremental part increment Z. The length of the activation vector is denoted by D. The authors discuss the circular convolution operator, its equivalent circulant matrix, and its calculation in the frequency domain. They leverage the circulant structure of C, increment W, to achieve efficiency, diagonalizing it by the Fourier basis. The authors also derive the analytical derivatives of the loss function L with respect to increment W and X, utilizing the chain rule and commutative property of circular convolution. Finally, they introduce blockwise convolution for controlling the number of trainable parameters and analyze the computational complexity of C3A. The proposed approach, C3A, introduces a novel parameter-efficient fine-tuning method for large neural networks, leveraging circular convolution and its associated circulant matrix to model the delta weight matrix. To enable flexibility in case of difficult downstream tasks, C3A resorts to block circular convolution, where the activation vector is split into blocks and each pair of blocks is assigned different convolution kernels. This approach requires B-squared convolution kernels, which can be represented by a block circular matrix. The number of learnable parameters is determined by the block number B, allowing for high-rank adaptation while maintaining a limited parameter size. A complexity analysis is conducted to compare C3A with existing methods, LoRA and Vera. The results show that C3A achieves a time complexity of O, BD log D, B, comparable to LoRA, despite its high-rank nature. Vera, on the other hand, incurs a prohibitive time complexity of O, RVD. In terms of space complexity, C3A requires no additional intermediate tensors, significantly reducing its space complexity compared to LoRA and Vera. The effectiveness of C3A is evaluated on various natural language processing, NLP, and computer vision, CV, tasks. For NLP, C3A is compared with several representative parameter-efficient fine-tuning methods, including BitFit, IA, 3, LoRA, Vera, and BOFT, on the GLUE benchmark with Roberta base and Roberta large models. The results show that C3A achieves better or on-par performance compared to baseline methods with extremely small trainable parameters. When a larger number of trainable parameters is allowed, C3A significantly outperforms the baselines. In the CV tasks, C3A is applied to fine-tuning the llama family models and evaluated on the traditional classification task using vision transformers, VITs, and the text-to-image generation task based on diffusion models. The results demonstrate the effectiveness of C3A in various scenarios. Overall, C3A presents itself as a compelling alternative to LoRA for model fine-tuning, offering high-rank adaptation while maintaining computational and memory efficiency. This research paper presents a comprehensive evaluation of various parameter-efficient fine-tuning (PEFT) methods on the GLUE benchmark. The authors fine-tune pre-trained Roberta base and large models on 6 datasets and report the performance metrics, including Matthews correlation coefficient, Pearson correlation coefficient, and accuracy. The results are presented in Table 2, which highlights the best performing methods for each dataset. The authors evaluate several PEFT methods, including BitFit, LoRA, Vera, BOFT, and C3A, and report their trainable parameters, memory cost, and performance on each dataset. The results show that these methods achieve competitive performance with varying degrees of parameter efficiency. For instance, LoRA and Vera achieve high performance with relatively low memory costs, while BOFT and C3A require more parameters but offer better performance. The authors also provide an extensive list of references, citing previous works on circulant matrices, circular convolution, and the discrete Fourier transform. They also reference papers on language models, visual prompting, and parameter-efficient transfer learning. The paper's focus on PEFT methods is motivated by the need for efficient fine-tuning of pre-trained language models, which can be computationally expensive and require large amounts of memory. The author's evaluation provides insights into the trade-offs between parameter efficiency and performance, which can inform the design of more effective fine-tuning strategies. The paper's technical contributions include the evaluation of various PEFT methods, the analysis of their performance on different datasets, and the identification of the best performing methods for each dataset. The author's work has implications for the development of more efficient and effective fine-tuning methods, which can be applied to a wide range of natural language processing tasks. This research paper discusses various methodologies and techniques related to fine-tuning in transformer-based models, particularly focusing on the use of adapters for efficient and effective model adaptation. The paper begins by citing several studies that have contributed to the development of state-of-the-art parameter-efficient fine-tuning methods, such as PEFT, Mengrolkar et al. 2022, which is an open-source library designed for fine-tuning transformer models. The authors also reference work on signal and system analysis, McGillum and Cooper, 1984, as well as research on controlling text-to-image diffusion through orthogonal fine-tuning, Chu et al., 2023. They highlight the importance of understanding the expressive power of low-rank adaptation, a concept explored in Zheng and Li's study, 2023. In addition, the paper mentions the role of residual adapters in learning multiple visual domains, Rebuffy et al., 2017, and the efficiency of adapters in transformers, Ruckelay et al., 2020. It also touches upon the idea of raising a child in large language models for effective and generalizable fine-tuning, Xu et al., 2021. Moreover, the paper discusses the GLUE benchmark and analysis platform for natural language understanding, Wang et al., 2018, as well as the use of circulant binary embedding for efficient and scalable learning, Yu et al., 2014. The authors also reference the bit-fit method for simple parameter-efficient fine-tuning of transformer-based masked language models, Ben Zakin et al., 2021. The paper concludes with a discussion on the expressive power of low-rank adaptation and its implications for future research. It highlights the importance of understanding the relationship between low-rank adaptation and the capacity of the target task, as well as the potential benefits of using householder reflection adaptation for bridging the gap between low-rank and orthogonal adaptation, Yuan et al., 2024. Overall, this research paper provides a comprehensive overview of the current state-of-the-art in transformer model fine-tuning, emphasizing the importance of efficient and effective adaptation techniques. It connects various studies and methodologies, showcasing the breadth of research in this area and identifying potential avenues for future investigation.